Humans don't read bytes. Why should our models? Have you ever been unable to fit common terms in your model vocabulary? We have a solution for you. Pixel representations allow us to address the vocabulary bottleneck, particularly problematic for multilingual models. We start from the same Unicode strings as traditional approaches, but in place of subword tokenization, we render strings as sentence-level images. We then use strided windows to tokenize this image into fixed size patches. From here, we jointly learn representations with the downstream task using a convolutional layer and linear projection to 5 12-dimensional vectors, similar to traditional embeddings. The rest of the model proceeds as usual. This approach allows us to have a dynamic input space without a fixed vocabulary. Traditional embeddings, on the other hand, require choosing a static vocabulary size in advance. Embeddings may be shared across languages if they have shared scripts and subwords. As we add languages to our model's vocabulary, capacity per language is reduced. This is particularly true if languages do not share scripts. With increasingly multilingual models, common words and characters can be out of vocabulary. Working in the image space, this is not the case, as pixels can be shared between languages with different scripts, and models have dynamic, continuous vocabularies. In addition to OOVs, different tokenization schemes result in dramatically different sequence lengths across languages based on encoding. This can affect performance across languages and multilingual models. Bytes and byte-level BPE, which are alternatives to traditional subwords, increase this disparity. Pixels, on the other hand, have lower variance across languages, more similar to BPE. Taking a closer look at two examples, we see that words with similar numbers of characters in the Latin and Devanagari scripts can have dramatically different numbers of underlying code points and bytes, while with pixels, they have the same number of tokens, just 3. Previous work has studied pixel representations for different languages in monolingual settings or transfer to a single language at a time. We here investigate the dynamics of multilingual training with pixels in a translation setting. Specifically, what is the impact of multilingual training with pixels? Do languages with similar scripts interfere with or boost performance? Are architectural changes needed with a larger input space in a multilingual context? And taking a closer look at cross-lingual transfer, are pixels more data efficient than the alternative subwords? On a many-to-one multilingual translation task with 59 languages, we see improved translation performance with pixels compared to BPE, which hold across 3 different common evaluation metrics. What is behind the improved positive transfer with pixels? We compare a variety of factors, and the most significant was the number of training examples for a given script. Looking at the 5 languages where we do the best and worst, we see this borne out. All 5 are low resource on their own, but for those languages with additional data for their script across our multilingual training set, we see significant improvements, much more so than with BPE. This is also true to a smaller degree for high-resource languages with high-resource scripts, where we see, for example, improvements of 5 blue for German to English. Without the source embedding matrix, our pixel-based models have about half as many parameters as traditional BPE models using the same transformer architecture. These parameters need to be added back to have equivalent model capacity, and we find that a larger and wider encoder gives us our best performance. We also find that our models are slightly more robust to potential over-parameterization. Check out more on this in the paper. Pixel representations are vocabulary-free. As seen in prior work, they can be directly fine-tuned on new languages and scripts without changing the model vocabulary embeddings. Using a smaller multilingual model trained on 7 language pairs, we investigate the efficiency and effectiveness of cross-lingual transfer to 5 languages with different degrees of vocabulary and script coverage and pre-training, from high coverage to an unseen script. Fine-tuning our models for each language individually, we find that pixels perform better than BPE for all 5 languages, with improvements increasing with reduced subword vocabulary coverage. Taking a closer look at Hebrew, we see that we also require fewer examples to get good performance, and further perform better than a BPE model with an extended vocabulary to include Hebrew. We also investigate a variety of other properties of multilingual pixel representations, which you should check out in our paper. Thank you very much, and thanks to my awesome co-authors. Our paper, code, and models are online, and feel free to reach out if you have any questions. Thanks.